So in Chapter 6, we're going to be looking at solving equations and solving inequalities. Strictly speaking, we're going to be looking at solving linear equations and linear inequalities. The techniques that we learn for solving these equations and inequalities may not necessarily work for other types of equations and inequalities. So you have to be a little bit careful, but you're not going to see those for quite a while anyway, so don't worry about it too much. So there's some general principles that we can follow, and one principle is to sort of do the opposite. We're going to be trying to isolate a variable and get to the point where we have the variable equal to some constant, some number. And you can ask yourself, well, what's happening to the variable? What are we doing to the variable? So I'm going to go through a few examples. The examples are pretty simple, but the techniques are very powerful. And you're going to be able to apply the techniques to much more complicated equations, but we need to start out with some very simple ones so that you get comfortable with those techniques. So let's say we have something like x plus 4 equal to 10. So we want to get to the point where we just have x equal to a number. You can see by observation, you know what that number is. That number is, actually this is x plus 4. That number is obviously 6. But how do we get there? So what are we doing to the x? We're adding 4. What is the opposite of adding? The opposite of adding is subtracting. So as long as we do it to both sides of the equation, we're fine. So we end up with x plus 4 minus 4. So we're doing that to one side of the equation. So then on the right-hand side, we have 10 minus 4. As long as we do the same thing to both sides of the equation, we're maintaining the truth of the equation. So when you add 4 and then subtract 4, it disappears altogether. You're just left with x. On the right-hand side, 10 minus 4 is just 6, which is exactly what we expected. If we have instead something like x minus 7 equal to 2, again, what are we doing to the x? We're subtracting 7. So the opposite of subtracting is adding, and we can do that to both sides of the equation. So here we have the plus 7 on the left, the plus 7 on the right. And as long as we do the same thing to both sides of the equation, we're safe. And on the left, when you subtract 7 then and add 7, it disappears. So you're just left with x equal to 9. And you can go back and look at the original equation and just check that that is true. If you replace the x in the original equation with 9, 9 minus 7 on the left becomes 2, which is the same as the right-hand side. And that's ultimately the goal of what we're doing. To solve an equation means to find the value of the variable or variables, once you get to equations with more than one variable, that make the original equation true or make the statement true. Let's take a look at a slightly different equation. What if we have 5x equal to 20? So here, what are we doing to the x? We're multiplying it by 5. Well, what's the opposite of multiplying? Opposite of multiplying is dividing. So if I take the left-hand side and I divide it by 5, as long as I do the same thing to the right-hand side, divide it by 5 as well, then we're fine. The 5's on the left-hand side cancel out, leaving us with just an x. And on the right, 20 over 5 can be simplified to 4. If I take that value and I plug it into the original equation, I should get a true statement. On the left, I have 5 times 4, which is 20. On the right, I have 20. So that's a true statement. What if, instead of multiplying the x in the original equation, I'm dividing the x by something? So x divided by 3 is equal to 4. What's the opposite of dividing? Multiplying, just as we saw. So here I want to multiply both sides of this equation by the same thing. And keep in mind that you can multiply both sides of this equation by anything you like, but the goal is to get x on its own. So if we want to get x on its own, the only way we're going to do that in this case is by multiplying both sides by 3. So again, the 3's are going to cancel, and we're going to be left with x on the left, and on the right, where 3 times 4 gives us 12. Once again, if you go back and you plug that into the original equation, on the left-hand side, you have 12 over 3, and that simplifies to 4, and that's the same as our right-hand side. Now, all of this seems almost overkill, because in every one of those examples you could probably have just solved it by observation, which means just looking at it and figuring out what the number is. Your brain's pretty good at solving these simple equations without using any of these techniques. But it is really important to learn the techniques so that when you get to more difficult equations that are difficult to solve by observation, you'll be able to do it using these techniques. So let's take a look at a slightly more difficult equation. What if we have 2x plus 5 equal to 13? Now, when you ask yourself the question, what are you doing to the x? You could say, well, you're multiplying the x by 2. You're also adding 5 to it. Now, strictly speaking, you're not adding 5 to the x. You're adding 5 to the expression 2x. But nevertheless, there seems to be two different things going on here, and therefore two different ways you could proceed. And in fact, both ways that you could proceed are perfectly valid. But one way is going to lead to more mistakes. Let's just take a look at the two different ways we could approach this problem. We could say, let's deal with the plus 5 first. What's the opposite of adding 5? The opposite of adding 5 is subtracting 5. So if I take that left-hand side and I subtract 5, then as long as I subtract 5 from the right, I'm okay. The plus 5 minus 5 disappears, leaving me with 2x. And the 13 minus 5 on the right becomes 8. And now I can ask the question, what am I doing to the x? I'm multiplying by 2. So the opposite of multiplying would be dividing. So I divide the left by 2, and I divide the right by 2. And I end up with x equal to 4. If I take that value and plug it into the original equation, 2 times 4 plus 5, well, that's 8 plus 5, which is 13, which is exactly what we get on the right-hand side. Now, let's take a look at the other approach. The other approach would be to deal with the fact that I'm multiplying x by 2 first. So the opposite of multiplying is dividing. So if I took that left-hand side, 2x plus 5, and I divided it by 2, and then I took the right-hand side and I divided it by 2, this method is going to lead to the right answer if we're careful, because the result on the left-hand side is that the 2x over 2, all right, we can treat that as one fraction, but we also have 5 over 2. Now, 2x over 2 just becomes x. But the problem is now we're dealing with fractions. And when you're solving these equations, it's much, much easier to deal with integer operations. And there are techniques to minimize the amount of time you have to spend working in fractions. Sometimes you can't avoid it, but we're going to see there's lots of different ways we can turn equations that have fractions into ones that have integers, and then deal with the integers for as long as we can, even when the final result, the final solution, involves a fraction. So here, before we learn those techniques, let's just say, well, now we're adding 5 over 2, which is 2.5. If we subtract that from both sides, that's okay as long as we subtract it from the right-hand side too. And so we end up with x equal to 13 over 2 minus 5 over 2, which is 8 over 2, which of course simplifies to 4. So, we get the same answer in the end, but whenever you have these choices, it's best to try to choose the choice that only leads to dealing with integers. And in general, that means adding or subtracting first, but we're going to see it's not always the case. So let's take a look at another example. In this case, we have 3x minus 4 over 5 equal to 6. So, we're doing a whole bunch of things to the x here, right? We're multiplying it by 3. Then that expression 3x, we're subtracting 4 from it. And then that whole expression 3x minus 4, we're dividing it by 5. So what do we deal with first? Well, here's one sort of rule of thumb that I like to follow, which is that whenever you have fractions in your equations, try to take some steps to get rid of those fractions. So that denominator of 5 there, I'd like to get rid of. How do I get rid of it? I do the opposite. Instead of dividing by 5, the opposite would be multiplying by 5. So if I multiply the left-hand side by 5, I'm going to get rid of the fraction on the left, and then I need to multiply the right-hand side by 5 as well. So these 5's cancel out, and I'm left with 3x minus 4 on the left, and 5 times 6, which is 30, on the right. Now I've got a nice equation, no fractions, and it's a lot easier to deal with. And once again, if I divide by 3, I'm going to end up having some nasty fractions to work with. The minus 4 over 3 is not something I really want to work with. So let's deal with the minus 4 first. And the opposite of subtracting 4 would be to add 4. So if I add 4 to the left, I'm okay as long as I add 4 to the right. And so I end up with 3x on the left and 34 on the right. And now I can take the final step, which is to divide both sides by 3. And I end up with x equal to 34 over 3. Now 34 over 3 can't be reduced. It's a common fraction. And I think it's probably the best way to leave this solution, 34 over 3. However, you could say, well, it's 11 and a third, so a little bit bigger than 11. And for the purposes of plugging it back into the original equation, you might find just estimating to be a good strategy. Trying to plug in 34 over 3 to the original equation is going to be perhaps a little bit more work than you really want to do. If you have the time, though, you should try it, and you'll find it's actually not too bad. So we ended up with a fraction at the end there, but most of the steps in this whole process involved integer operations. And I would say if you want to minimize your chances of making a mistake, you should always be trying to work with integer operations. Let's take a look at just one more example. And these are two questions that are actually in the homework for the textbook. So I'm going to put them up and kind of do them one on the left, one on the right. What if we have 5x minus 7 equal to minus 15? So let's put a minus in there, minus 15. And then another one, 2m plus 4 equal to 11. So they both kind of look similar, right? And yet I'm going to make different choices here. So we could expand the left-hand side in both cases. So on the left, the equation would become 5x minus 35 equals negative 15. On the right, we'd get the equation on the right, we'd get 2m plus 8 equals 11. But I'm going to tell you that while expanding on the equation on the left, we'll keep everything in integer form. We'd also like to keep the numbers as small as we can. And because the right-hand side is a multiple of 5, I would say that probably the natural first thing to do here would be to divide both sides by 5. If I divide the left-hand side by 5, I sort of save myself some effort here. I've got to do the same thing to the right-hand side. So the 5's cancel out, and I'm just left with x minus 7. And the minus 15 over 5 simplifies to an integer, minus 3. And now all I have to do is add 7 to both sides. And I end up with x equal to 4. I can check that to make sure that it works. I plug it into the original equation. 4 minus 7 is negative 3, times 5 is negative 15. Now, on the right, I don't want to follow the same first step. And the reason is if I divide both sides of this equation by 2, I'm going to end up with a fraction on the right, 11 over 2. And so now I'm not going to be dealing with integers. So you need to kind of explore this flexibility and realize that you have certain choices. And it isn't that one is right or wrong, it's more that one is going to make life a little easier than the other. So if I expand the left-hand side here, I get 2m plus 8 equal to 11. And now I can say, all right, the easiest thing to do is to deal with the plus 8, and I do the opposite, which is subtracting 8. So I end up with 2m equal to 3, and then finally I end up dividing both sides by 2, and I end up finally with m equal to 3 over 2. And again, because the final solution there is a fraction, it's a bit harder to plug it in and check this, but definitely worthwhile doing. And notice that all the steps we took just involved integers, even though the final solution was not an integer. So you need to practice these over and over again, both to cement the techniques and also to start to have an intuition as to which steps to do first to make life as easy as possible.